So hopefully, some of my content can echo what the speaker has mentioned earlier. And so today's, I'll be specifically talking about a couple of interesting things. One is related to natural language generation, evaluation, but I will also talk about reasoning, right? As this was in the last talk and in many of the previous talks, and talk about how do we do evaluation for NLG when there is complex reasoning involved. All right, so why do I talk about evaluation for natural language generation specifically today? As you know, I think there are a lot of problems in NLP. We have evaluation issues, but NLG, in my opinion, in my past 10 years in natural language processing, I do believe that this is actually one of the most challenging evaluation problems in NLP. And I'll tell you more, and I'll tell you why this is the case. So as we know that we've been using a lot of this lexical overlap-based evaluation, and BLUE was invented a long time ago, right? But then it is still dominating. And I think, the issue is really that it was inappropriately used in many different ways in very different tasks, in addition to machine translation, right? So, machine translation was originally was designed, right? The BLUE was designed for machine translation, but unfortunately, some of these lexical overlap evaluations also went to other NLG problems, and I'll tell you why there's an issue. And the other thing is that there's this diverse nature of all these downstream NLG problems. For example, data to text generation. We also have visually grounded generation problems like image captioning, video captioning, and there's summarization, dialogue, and of course there's machine translation. So if you look at all these different applications, there are a lot of differences among these different tasks. And how is that difference actually influencing the evaluation? Well, that's actually a very interesting thing that we'll talk about today. And more specifically about the challenges in natural language generation evaluation, I think first we need to think about why there's the issue with this lexical overlap-based approaches, for example, BLUE or Rouge, right? So one thing I think everybody for sure knows is that it doesn't really capture the semantic matching between the reference and the generated content, right? So this is very well known. And the other thing I think people recognize in the past few years is that it often fails for long text generation problems when the text of the reference and the generated content grows, right? So this problem actually becomes a much bigger problem, because imagine that you can rearrange the lexical items in the content. So that becomes a bigger issue, right? Because you can pretty much rearrange the reference and rearrange the generated content and get very different semantic meanings, but still you will get the same BLUE score or Rouge score in this case. The other thing I want to talk about in the second part of the presentation today is to talk about the importance of looking at sample variance and why variance-free reporting of these results will amplify the issues that I mentioned. Because as you can see that often in machine learning papers, in machine learning conferences, standard deviation or standard errors are reported in some of these empirical papers, whereas in natural language generation, what we found is that most papers don't really report the variance, which creates another complexity to this problem. And the last part, I will talk about another challenge, which is when your generation problem gets more complicated, that involves reasoning, that involves logical understanding of your input data, there's even a bigger issue with the existing evaluation problems that we run into in natural language generation. And specifically, I'll talk about adversarial examples, and I'll talk about if you need to verify the factualness in the generated text, how can we actually try to evaluate this? All right, so specifically, I'll talk about three things. The first part of the talk is that I'll go through metric learning. I'll talk about how do we actually automatically learn the metric instead of defining a metric. So this is our earlier work in ACL 2018 on inverse reinforcement learning for visually grounded storytelling, right? So how would you be able to model the objective and model diverse answer? So instead of using blue or rouge to train your model, can we learn the metric at the same time when we're generating the policy model? And the second thing I want to mention, like I said, is to look at sample variance for diverse set of problems in language innovation generation. Finally, I will talk about logic NLG, which is our recent work on looking at semantic parsing and adversarial example for evaluation in table-to-text generation. So here's the motivation that I just talked about, and we'll dive into inverse RL for visual storytelling and in evaluation. Then I'll talk about understanding sample variance in natural language generation evaluation. Then I'll talk about reasoning and how do we understand reasoning-based generation and also the evaluation. Finally, I will talk about the conclusion. All right, so let's dive right into the first part, which is metric learning, right? So why is metric learning important? Because while you can actually use the metric learning in the training procedures as well, right? In addition to the evaluation. And just to brief remind you that what these existing overlap-based evaluation metrics are, in general, is that you need to have a generated candidate, right? And a generation candidate and some human references, right? Could be one, it could be more, but output is often a score. For example, if you look at blue, then this is precision-driven congruent overlap, right? And then rouge is recall-driven congruent overlap, and meteor is weighted F1, and cider is TF-IDF plus cosine similarity. So meteor and cider, especially cider, is more commonly used in image captioning and video captioning. So I'll give you one example of what a generated text looks like, and you can tell me what you think about this, right? So how about if you assume, right, that we have reasonable references, what is the meteor score of this sample output, right? So this is visual storytelling, assuming that I gave you some images and the references are also reasonable and there's the generated text, right? So what do you think the meteor score would look like for this particular example? Well, the answer is, well, the actual score is pretty high, right? So this doesn't make much sense because if you look at this particular story that it was generated, it doesn't really make any sense, right? So a lot of stop words and really looks like, you know, some sort of this neurogenerative model that keep generating high frequency words. And at the end of the day, if you compare the meteor score with the reference, you get a score of 40.2, right? So even higher than the state-of-the-art models like 35. So it looks like you generated the best story, but actually they're not very readable, right? So this shows clearly some of these metrics are broken when you're evaluating long tests, right? So basically your system trying to maximize the overlap between your reference and your generated context, but unfortunately you would end up a story that is not quite readable. So how about this one instead? Now, this is also an interesting example because if you read a story, right, and the story looks pretty good, right? So I had a great time at the restaurant today. The food was delicious. I had a lot of food. I had a great time. And if you look at three images, so this is the paragraph automatically generated by one of our systems. And if you use traditional evaluation metrics like BLUE score, well, this just gives you a BLUE score 4 of 0, right? So foreground BLUE score of 0. And this also doesn't make much sense because even though this might not be the best story you've ever seen, but it is still a very reasonable generated result from these three images. So something is clearly broken, right? So what's broken? So we need to look into the details. So that's why we introduced, in 2018 ACL, we introduced this adversarial reward learning approach that says, well, for this complex visual storytelling task, the challenge is really how to quantify a good story. And the classic metrics like blue, rouge, or media, a cider, they don't really work well, right? So how do we actually learn a policy while learning the reward function? So that's the important part, because it's not just your evaluation is broken, right? Your training could also be broken when you see longer paragraph. So clearly, when the task is trying to generate a long paragraph, then we need to think about not just the evaluation, but also training as well. So we came up with this adversarial reward learning approach that in addition, just to optimize the policy for generate a story, once we fix a policy, we also try to improve the reward function, which is basically a convolutional neural network that generate a score that we can use this as a reward to improve the policy model. So this is what the figure looks like, right? So as you can see here, in the environment, we have pairs of images and references. So instead of just train a policy model that takes stories and use images, now we learn a reward model with adversarial learning. And this part is what we call inverse reinforcement learning, that in reinforcement learning, typically what you do is that you fix the reward, right? And then you learn the policy to generate text in this case. But inverse reinforcement learning is that we have this adversarial objective and we're trying to fix the policy model. So assume that initially you have a good policy model, right? Or a reasonable policy model. Then we can basically use this pre-trained policy model to sample story, and we can take the image pairs and reference from the ground truth human written story and evaluate the quality of the sampled story so that we can compare with the pairs in the environment and to update our reward model. So in this case, the hope is that once you have a better reward model, then we'll be able to generate a numerical reward, and we can take this reward, right, and fix the policy, fix the reward model and update the policy model. So it's a two-step policy learning process that once we fix the policy model, update the reward, and we can also fix the reward and update the policy model. All right, so then we need to think about what kind of baselines we can compare, right? So in addition to cross entropy loss, mixer is something that a lot of us are familiar with, right? So this is basically by looking at, in addition to cross entropy loss, we can also look at blue score directly, right? Using the reinforced algorithm that we can iteratively updating the cross entropy loss, but also updating the blue scores, right? So you can look at the generated text comparing to the reference, and basically this will give you additional feedback in the form of reward so that you can update your policy model. Like I said, for this problem, a major challenge is the evaluation, because I said clearly broken metrics include media, blue, and so on and so forth. So how do we do the evaluation? Well, at the end of the day, we'll have to turn to Mechanical Turk to do the aerial storytelling evaluation. And we're using the VIS data set from Wang et al. 2016. And in this Turing test, basically we ask the crowd to decide, here's human, here's generated text. We don't tell you it's generated text or not, right? Here's basically a pair, right, of the story. So one could be generated, right? One could be machine written, but we don't tell the crowd which one is which. So we let the crowd to decide, right, whether this is generated by human or whether this is generated by machine. And we can even do this pairwise evaluations, right? And ask people to pick which one is generated by machine and which one is generated by system. So at the end of the day, we will be able to look at the number of cases, right, that people on Mechanical Turk got confused with the evaluation result. So if they think the story is generated by human, but indeed it was generated by machine, so that in this case, we say that the system wins, right? That the system successfully generated high quality text that confuses the human judge. And we can basically look at the number of cases that each method win, right? And then we can look at the cases that people are unsure. And basically, if you look at cross-entropy loss, CIDR-based reinforcement learning, and BLUE-based reinforcement learning, we can get to a certain performance. But with the aerial-based approach, we can get to about 45% of cases that people actually chose real generated story as better story, right? Comparing to the human generated text. So I think this is kind of interesting evaluation we can conduct instead of just asking people to give, Likert scale rating to do this task. For the first part, I also want to say a few words about when we think inverse reinforcement learning can work, right? So why do we do metric learning, right? So I think it's important to consider the situations where the optimization target is complex. So let's say if you're training a reinforcement learning agent to do Super Mario games, right? Then there's no point of doing IRL because you actually see the rewards changing, right? Every single step. Let's say you eat a mushroom, that your score maybe change, right? So in that case, there is no point of doing reinforcement learning in the form of inverse reinforcement learning because you clearly get the reward and that's a very accurate reward. But whereas in storytelling, right, people have different, impressions about what the story might be. So there's no easy formulation of the reward. It's very difficult to directly express that in the objective function or in the evaluation. So that's why in the cases that we cannot clearly define the reward, we can try IRL, whereas the opposite, if you can clearly define the reward, then don't try IRL. All right, so this is first part of the talk. I will continue into the second and third part, so feel free to type your questions in the chat channel and happy to answer any questions towards the end of the talk. And the second thing I want to describe is our more recent work of looking at sample variance, right? So this is EMNLP 2020. And again, we're looking at this visually grounded language generation problems, and we're interested in understanding more about sample variance. So what does sample variance mean? Well, in this case, you can imagine that if we get some human annotators to write the references for a summary, well, let's say for a soccer game, some people, right, may actually look at the score. Some people may actually look at the games, the teams, and some people may look at the red card or yellow card, and some people may look at in general, the ranking of the two teams in the league. So people may have different utilities when working on this task. There may be some, variabilities in generated these references. So the question is, how will this generated summary reflect, right, this variability in human generated references? So here's one example, right, of visually generated language problem. So one is image captioning. I think people are familiar with this since 2015. Video captioning is more recent and is more challenging because there's the dynamic decision-making process that you need to incrementally decide, right, which frame and which action you need to generate. Visual storytelling is the task that I just talked about in the previous section, that given a set of images, your goal is to generate a paragraph of what's happening in the set of images. And I just briefly mentioned the issue, right, with variability in the human references. And this is a clear example of what the variability is. And this is an image captioning task. And we have 5 references here. And you can clearly see that in this very diverse image, there are a lot of objects. and our annotators clearly mention a whole bunch of different things, a whole bunch of different objects in this image, and we highlight them in different colors. And as you can see, there are very different set of images, different set of objects in each of the references. And some of them, they don't overlap. Some of them, like the runner, actually get overlap. So the question is, for natural language generation, specifically in visually grounded generation, if we have this diverse set of human generated references, is this good or bad, right? Is this showing some sort of consensus, or how can we use this to do the evaluation? So that sort of motivates us to systematically study 3 visually grounded language generation problems by looking at 7 data sets and 6 automatic evaluation metrics, right? And some of them I already talked about, right? Blue, Rouge, Meteor, and Cider. But there's also Spice and BERT score, right? BERT score is specifically, I think, relatively new and interesting because instead of looking at lexical overlap, it uses BERT model to look at the distributional semantic similarity between the references and also the generated content. So BERT score is obviously different from the rest of the group. And as we can see in the 3 different tasks, image captioning, video captioning, and visual storytelling, we're looking at number of different sources and also very different number of references for each particular example in the training and evaluation set. So the first question we want to ask is, what about the reference variance, right, within data set? So one experiment we can do is to look at consensus. And how do we look at a consensus? Well, typically what we do in this metric is that we look at overlap between the generated sentence and the references, right? So we look at machine output with the human output. But in this experiment, what we can do to look at the variability is to take one human reference and use this one human reference to verify against other human references and to look at overlap, right? So this will give us an idea if there's any consensus among the annotators. And if there's no overlap, well, then it might not be good, right? Because it could be challenging for machine, right, to generate the reference as well, since there's no agreement whatsoever for this task. So here we're looking at all these different metrics, and we're looking at the consensus metric score. And one thing I think is observable is that if you look at the BERT score, right, the BERT score actually correlates with the task difficulty very well. So for example, as you can see, visual storytelling is the most difficult task because you're generating long paragraph and you get a BERT score of only 15, right, in this case. Whereas image captioning is a single image, and in general, you get high 50s, some low 50s. But for video captioning, it's more challenging. Regardless of language, your BERT score is actually lower, right? It's about 40 to 50. And this is essentially showing some of the agreement within this data set and how is that related to the task difficulty. And if you look at BERT score to estimate the consensus metric, and we can see that there's a clear alignment between the task difficulty and the BERT score. The other thing I think is rather surprising is actually Cider, right? So a lot of you been using Cider for video or image-based language evaluations, and turned out that Cider has a large standard deviation on the consensus score, regardless of what particular data set you're looking at. And here you can see that clearly this error bar is actually quite big, right, for this consensus scores on all of these different data set when you're looking at Cider. And Cider is based on, like I said, TF-IDF and cosine similarity. The second thing we want to check is the effect of sample variance on evaluation performance. And what do I mean by that? Well, one thing you can look at is specifically look at references per instance, right? So in this case, it's references per visual instance. So the question is, how many references you need to collect, right, for each example. And in this case, we're looking at the testing RPI, which is basically in the testing time, right? How many references per instance do we need to get a stable result? And this is interesting because, again, if you look at some of this data set, we see that we do need to worry if we only have a few parallel testing references in the test set. So in these two figures, as you can see, if we have less than 10 references in the test set, then you should really worry the result, because if people not showing the reference, if people not showing the variances in the evaluation result, and they have less than 10 references, some of the result can actually be very unstable, right? In this case, if you look at SIDA, the score actually varies a lot, right, in different runs, but when you're looking at different references. And even with more references, you can see this sort of stabilized, right? When you have 30 to 50 references, then you have more reasonable, more stable SIDA score when you're looking at the testing situation. And I think this is also the same on, the standard deviation, right? So for all of these different metrics, in addition to SIDA, as you can see, has very high variance. But for other ones, I think it's also general rule of thumb. Try not to use less than 5 or less than 10 references in your test set, because again, the numbers I reported in this paper could be 30, but the standard deviation, they don't report it, but it can be very big, right? It can be 5 or 10. Then it actually make all of the claims in this paper as invalid. So the other thing I think is interesting to think about is to think about the problem of, do we need more instances or do we need more references, right? So in this case, it's more visuals comparing to references. So when we talk about visual, we mean, for example, in image captioning, do you need more images or you need more references per image, right? So in this experiment, one thing we can easily do is to look at the training reference per image, right? So do we increase the size of the references and get similar result, or do we not, right? So in this case, again, I think it's very complex figures, but you see the trend, right? So when we actually increase the number of references per image, but we keep, right, the general size of the training set static, right? So we don't change the size of the training set, but we increase the number of references per image. And as you can see, for image captioning, for video captioning, the performance actually dropped, right? So in some sense, what does this mean? It means for image and video captioning, the system do want to see more images and more videos, right? So in this case, you will get better performance. But if in this case, in the training time, you provide a lot of references, this might not actually help you to improve the performance for this task. Whereas there is actually a major difference is that if you look at the storytelling application, the observation is completely different, because like I said, storytelling is a very difficult problem. And if you want to train a more stable and better performing storytelling model, you need to actually increase the number of references in this case. And we see that if you increase the size of references in the training set, that actually improve the result, as opposed to decrease the result in image captioning and the video captioning. So this is very interesting observation. So there are some practical takeaways in the second part before I move on to the third part. And I think one practical takeaway is that if you're looking at this classic, blue or rouge-based evaluation, please report the metric score together with the variance, right? Because if you don't show the variance, it's very difficult to understand the stability of your result. And in some cases, if you have smaller number of references per instance in a test case, then you will have high variability in the evaluation. The other thing I want to mention is that if you are going to collect a new data set, right, then you need to think about whether you should include more human references or you should include less human references, for instance, to improve the evaluation. And what we observe is that this really depends on the application, right? So in storytelling, as you can see, it's a difficult task, so you need more references and it's a longer text. Whereas in image captioning and video captioning, this is not the case. So this is really depends on the complexity of the problem you're trying to solve. And finally, I think it's also important to think about the testing situations when you are designing a new data set. All right, so the third part of my talk, I'm going to continue the discussion in natural language generation evaluation and specifically look at a difficult situation in logic-based natural language generation. So why am I interested in logic-based natural language generation? Well, because the existing NLG paradigm sometimes is just, adding context, right? It's very straightforward, it's converting data into surface form, and there's really no logical reasoning or inference involved in the generation, right? And in this particular talk, and I will tell you a little bit more about our recent work in logic-based natural language generation, such that we can look at reasoning with complex objects in the input space and to generate more interesting and more complex sentences in NLG problems. And specifically here, I'm talking about this ACL 2020 paper, Logic NLG, generation from open domain table. So this is more like a data to text generation problem where the input is a table, and I do want to generate natural language sentences about the correct statements, right, in this table. So here's one example, right? So this is a table from a tournament, and you can see there are these different countries, and there are different number of medals in gold, silver, and bronze. And they're talking about different sports here. Classic generation, right? Like I showed you earlier, classic generation problems often just look at the surface level generation. So for example, this one, the system will just generate Canada has 3 gold in the tournament, and Mexico got 3 silver and 1 bronze in this tournament, right? So this is straightforward synthesis from the table. So there's no change, just taking one column, one row, and basically look at the cell content and to generate, straightforward, fill in the blank, right? That what is the general result. So this is widely used in some of the automated systems in, algorithmic writing, right? So for example, in earning calls or in sports that people are already using this surface-based generation, just fill out the score, fill out the earning result, and then you have news articles. So very easy to do, highly accurate, but also in some sense a little bit boring, right? Because you can also read those from the table while you're generating unstructured text, right, for these cases. So that's why we actually try to make it more interesting and propose this logical-based natural language generation problem. So in this case, instead of direct synthesis from the input data, now how about we teach machines to generate Canada obtained 1 more gold medal than Mexico, right? And Canada got the most gold medal in the game, right? So this is interesting because you can't really easily tell, right? If you're a machine, you cannot easily tell that this number directly copy paste from one of the cell. Then we require machines to perform reasoning with text and tables to actually generate the correct outcome that is factual and faithful to the underlying data. So in order to do this, we'll have to collect a data set. And specifically, we look at Wikipedia open domain tables, and that allows us to have rich inference over numbers, dates, and text. Some of these tables, as you can see, is definitely not very well structured. So there are texts, there are unstructured texts, and in general, it's sort of like semi-structured resources that we're looking at relatively large data set and a relatively large open domain table to text generation in this particular case. All right, so what are some evaluation challenges? Well, like I said, the key here is fidelity, right? Or what we call faithfulness, in the sense that you can't really use the standard, blue or rouge-based evaluation at the end, because in this case, you might not reflect the factual correctness, right, according to the underlying table. So we do really need to make sure that the text and the content we generated are factually correct, right? So this has a higher requirement than just lexical overlap with the ground truth. And in this case, we tried some information extraction-based evaluation, and it's very difficult because once we're doing the surface level, information extraction, we do logical reasoning, but again, very difficult to extract the triple with the existing information extraction-based approaches, and very difficult to compare and verify the correctness and the quality of this generated context. So IE-based is in general very difficult. The other thing we can think about is that if you have an in-domain semantic parser, right? So in this case, if you have a Wikipedia semantic parser, one thing you can do is to basically use the semantic parsing techniques to try to do semantic parsing like we did in KBQA, and then take the semantic representation to query your table, right? To query that your structured data representation. And if that basically return true, then it means that the fidelity is preserved in the generated text in your evaluation. But if it return false, it means that this is not possible. But you can see easily there are pros and cons with semantic parsing techniques in this evaluation, because you do need to have a reasonable semantic parser for this in-domain text. So otherwise it's not gonna work, right? But if you have a reasonable semantic parser in this particular domain, certainly you can use this to evaluate the factual correctness with the generated sentence. The other evaluation I think is interesting that is relatively new in natural language generation evaluation, specifically in factual NLG problem, is to look at adversarial evaluation, right? Because the original text I show you is that Canada obtained 1 more gold medal than Mexico, right? But what about you tweak, right, the 1 more gold medal into 1 less gold medal, right? So this becomes an adversarial example that is obviously false, right? So if you can send both of these two sentences into your generation model, let's say GPT-2, right? And then you can look at the probability of this particular sentence condition on the table. So looking at the probability of this correct sentence condition on the table, and you look at the probability of the adversarial sentence condition on the table. And the hope is that if you have a good generation model, right, then your system should score a correct sentence, a factually correct sentence, higher than the adversarial examples, right? So this is the idea of adversarial example in logical NLG evaluation, that assuming you have a reasonable generation model like GPT-2, now basically you can feed that adversarial example and the correct example to your model, and we can look at the scores. And the idea is that the correct ones should have a higher score. So that's basically the adversarial-based evaluation. I will also tell you a little bit about other challenges in this logic-based NLG problem, so that you understand a little bit more about why the classic evaluation might fail, right, in this case. And I think one challenge is the classic left to right generation, right? Like beam search or greedy search. And for example, in this case, right? So if you start with Columbia has like 2 or 4 or 5, well, in this case, if you generate a number you sort of already decided, right, of what logical operation you're looking at. Are you looking at the differences? Are you counting all the total metals, or what else are you looking at, right? But if you actually generate a wrong number, then we don't really know how you come up with number 5. And also, if you generated 2 already, then it seems weird because you don't really know what countries you're comparing in this case, right? In this first example. So left to right generation sometimes doesn't really work very well when you're looking at complex generation problems, because you could actually get you into trouble, or it can actually help you to with some of this specific type of logic. But we found this to be particularly challenging when you're looking at left to right generation for logic-based NLG, because if it's already fixed in earlier tokens, then it's a little bit difficult, right, to actually determine what kind of operations that you want to generate. And specifically, some cases that people have that intention in mind, that you want to generate this specific type of logical operation, and that case is also difficult to go from left to right. All right, so yeah, so we already discussed this, right? So there's no rigorous definition about logical order or linguistic order, but main point is, in general, it's difficult, right, to be able to think about the agreement from left to right generation order with the logical inference, right? The steps that you have in logical inference. And one solution, I think, along this line is to think about the coarse to fine generation, right? So for example, if you have a template and you can actually try to use this template to mask entities and numbers, and then you use the GPT-2 model to basically first generate a template, and then trying to go from the template to fill in the blank, right? So this could be a coarse to fine generation solution to deal with this issue. And of course, I think there are a lot of recent work in the machine learning and NLP community on going beyond monotonic generation. So for example, you can look at non-monotonic generation to deal with this issue that, instead of going from left to right or right to left, you look at the logical order. Of course, logical steps is hard, right? So because you have to get people to get the annotation. Otherwise, it's also difficult to train this kind of models. But one solution you can look at is to look at a weakly supervised manner, that you have a pair of question and answers, but maybe you'll be able to find out the generative process in non-monotonic generation process. All right, so the brief conclusion about the third part is that I think logic NLG is very interesting to look at factual based evaluation for natural language generation problems. And it asks a lot of different questions on semantic parsing and also examples, and how they may actually help in NLG evaluation in these very complicated generation problems. And I think particularly the fact-checking aspect and robustness aspect is universal in NLP evaluation. So to conclude the presentation today, first of all, if you remember that I talked about an inverse reinforcement learning strategy to think about this complex generation problems, that you can incorporate metric learning and policy learning all together in this generative process, and you can use mechanical Turk and Turing tests to do the evaluation. And secondly, I talk about the importance of sample variance and how it's related to different problems, and we also make some practical recommendations in going forward. And finally, in the last part, I talk about semantic parsing and there are several examples as alternatives to evaluate complex logic-based generation problems. And we do have these open challenges going on with TypeFact, Logic NLG, and Hybrid QA. And I invite you to participate in these open challenges to increase the understanding about natural language reasoning, natural language inference, and also the generation evaluation in these cases. And I think I just, run out of time. I want to thank all of my students for this wonderful studies. And I encourage you to check out our group page and also the open source GitHub repositories to download the source code of the projects that I presented today so that you can play with them and see if that help with your project. And with all that, I want to thank you for joining the seminar today and happy to answer any questions that you may have.
Thank you very much, William. Any questions? I didn't see any questions from Rocket Chat. So if you want to leave any questions, you can either just unmute yourself and say, or you could type in the chat box in Zooms.
Hello, William. I have questions about you have comments on this on the matrix design for the to test the reasoning abilities of logic in test. For example, so you can there's a lot of like generation model which can generate like math and like codings, right? So do you think what kind of like aspects or parameters do you think which are valuable to take into account when design a matrix to test the logics in test?
Right, yeah, that's an excellent question, right? So I think this is about the first part and the last part of the talk. And I think metric learning is interesting, right? But when you do metric learning or you automatically learn the metric, it is challenging, right? Because it is very specific to application. And I think one of the reasons why Blue and Rouge stay along for this many years is because you just need a Python or Perl script, right, to do the evaluation. It's very easy and very lightweight. They do not depend on any data set. They do not depend on any application. They don't really depend on any models you train. So I think that's the important part of defining a metric, that the metric should be independent, right, of the data set. And I think ideally it should also be independent of any model, right? So that's why I think there are some advantages in defining these metrics. But as you can see, there's also some recent work that build metrics specifically, right, depends on some model. For example, BERT score that I briefly talked about is a metric from Cornell University that instead of looking at lexical overlap, you look at this kind of like semantic overlap in the distributional semantic space, and you're using BERT model, right, to extract the numbers for each word, and then they try to compute the overall BERT score between a pair of sentences. So in that case, certainly it depends on BERT, but the good news is that at least BERT is a general purpose pre-trained language model. So there are some, abstraction in that model that it doesn't really depend on a particular model, right? So that's a good thing, because if it depends on specific tasks like text inference or fact checking or sentiment analysis, then it's very difficult to use it, right, across this different data set and different tasks. The second part of your question relates to fact checking and also the logical reading aspect. I think that's going to be more important going down the road for NLP testing in general, right? As you can see that the checklist paper actually won the ACL 2020 Best Paper Award, because more and more people realize that if you're using accuracy, if you're using Blue and Rouge, you can write a paper, but may not be able to ship the product, right? If you want to ship a product in a company, and you have to think about these unintended consequences, if it generates text that is not faithful to the underlying data distribution. Let's say in the situation that you have a conversational agent that you want to build, and you generate incorrect restaurant recommendation or incorrect location, then it would create a huge impact to your user. So certainly, I think, of course, like I emphasized in this talk, it depends on the application, but I think if you have an in-domain semantic parser, let's say in this restaurant recommendation domain or the travel domain, then potentially you can build a very high accurate semantic parser for this domain. And when you apply this to do fact checking or looking at the evaluation, you should be able to have very good consistency and very reasonable accuracy in evaluating the factual correctness, right, of this generated text. And the other thing, like I said, is interesting is adversarial example. You can either get human to write adversarial examples for you, or you can even try to use like Roberta or BERT to automatically generate adversarial examples for you. But then you need some form of human verification to make sure that these are actually adversarial examples, but not the correct examples, right? Yeah, so I think this distributional semantic based references and evaluations definitely will be important, but going forward, when we're designing new metrics, we should think about adversarial examples. And those are the cases I think we certainly need to avoid running into if we're going to ship any of these neural generative models in the real world products. And that's, I think, is going to be a super important aspect of natural language and generation evaluation.
Thanks a lot.
Any other questions from the audience?
Yes, I would have a question connecting to this last point of the adversarial example. So my question is, did you just point it out as a general, very important aspect, or I mean, do you have a specific paper in this context that you wanted to outline?
Right. Yeah. So I think, thank you, Stefan, for the question. So I think the logic NLG is the first time that we're looking at this complex logic-based generation and how we actually tried adversarial examples in this case. But as you can see, this is not the first paper, right, that actually consider adversarials in the evaluation. I think some of the earlier papers also look at adversarial example in general. For example, reading comprehension, right? So in reading comprehension, in the second version of Squad, that people started to look at adversarial examples in this content. And of course, there's the checklist paper that I recommended from the ACL 2020 best paper that a lot of you are aware. So I think, like I said, adversarial example is dealing with all these different aspects of NLP problems, and they're so critical to the robustness of, in general, the NLP applications. And I cannot emphasize more, right, on the importance of adversarial examples. But again, I think we need to think about how to come up with these adversarial examples, because if it's all human generation, right, it's also very expensive that you need to keep getting people, like really smart people, to come up with these corner cases to be able to test the robustness of the system in terms of this adversarial examples. But I think one thing we can look at in general, as we show in the Logic NLG paper, is that we can certainly think about flipping some of the keywords, some of the key semantic driven contents that actually change the meaning, right, of this entire sentence. For example, more into less, right, then you just completely change, right, the meaning of this sentence. So how do we automatically identify, right, these keywords, and how do we automatically trying to generate a large set of examples, adversarial examples, and then get human to look at them and fix them in our system? I think this is very critical, because I think one issue with this adversarial example is that they come from neural networks, right? So why does it come from neural network? Because neural networks are very good at exploiting the spurious statistics, right, in your data. So for example, many of you know that I don't need to give this example every time, but Stanford Natural Language Inference Dataset, right? So criticized by a lot of researchers because the way it generates the data, unfortunately, right, correlates with some domain. So that even though you're trying to use two sentences to tell the relationship between these two sentences, now in reality, you just need one sentence because some irrelevant words, right, relates to a label for this problem. So you just use one branch, you get very good result. So that's also kind of relates to adversarial example because the way you collected training data introduces the backdoors, right? Introduces the possibility of using adversarial examples to completely break that system that you built. It's very difficult to avoid because we're collecting empirical data anyway for any task and from different domains, but there's no way that you're gonna get all of the data. So what we do is empirical risk minimization. So collecting a subset of the data set in the real world, and inevitably you run into bias, inevitably you run into unwanted correlations between P, Y given X, right? So some unwanted words, and it's difficult to test and it's difficult to fix. So I think this is going to be an important issue going forward.
Okay, thanks a lot.
Any other questions? William, can I ask a quick question regarding the first parts regarding this inverse reinforcement learning?
Sure.
I'm aware that that work appears in 2018, so it's before BERT or the contextualized embedding things become so popular. And after BERT becomes so popular, many works started to use BERTs or similar technologies to learn rewarding functions. So what would you say is the pros and cons between the reward functions learned by IRL and the rewarding functions learned by supervised machine learning things like BERTs?
Yeah, thank you, Yang. This is an excellent question, right? Because after that 2018 paper and after BERT, we actually had an EMNLP paper from last year, EMNLP 2019, that we use this distributional semantic rewards like a BERT score, right, as a reward for summarization. And it actually worked out really well, right? So because of the strong representation learning capability, now you can better capture the relationship between the generated text and the output. So we actually try to use BERT as reward to do summarization in the last year's MLP paper, and we got really good result. But again, I think there are cases that BERT might not always working, right? For example, in some of the visual domains, in some of the structured data, right, like tables and also other forms of the data set. So in text, it works really well, but I think in some of the complex problems where you have heterogeneous inputs, then still we need to think about IRL. We need to think about how to integrate BERT as a strong pre-trained language model into the text components, but also help to look at the tasks in general and also other input modalities.
Thank you very much. I think we are running out of time. If you have any additional questions, please feel free to put on Rocket Chat, and we're going to forward them to the speakers. Thank you again, William, for the excellent talk. Thanks for coming.
Thank you. Thanks for having me. Bye-bye.
Bye.